Water does not naturally flow uphill. Oil does not push itself through kilometers of pipeline. Coolant does not circulate inside an engine on its own. Whenever liquid moves against gravity, against pressure, or against friction, one device is responsible: the pump. If you like similar educational content, please like, subscribe, and share the video with your friends. A pump is a machine that converts mechanical energy into hydraulic energy. In simple terms, it adds energy to a liquid so that the liquid can move from one place to another. But what does adding energy actually mean? From a physics perspective, any moving liquid carries three forms of energy: pressure energy, kinetic energy, velocity, potential energy, height. In a closed system without external input, the total energy of the liquid remains constant, minus losses. A pump changes that balance. It injects mechanical work into the system and increases the total energy of the fluid. That added energy allows the liquid to rise vertically, overcome friction in pipes, maintain circulation, or achieve higher pressure. It is important to clarify a common misconception. A pump does not suck liquid. When we say a pump sucks water from a well, what really happens is that the pump lowers the pressure at its inlet. Atmospheric pressure then pushes the liquid into the pump. Because atmospheric pressure is finite, there is a physical limit to how high water can be lifted by suction alone. For water at sea level, that theoretical maximum is roughly 10 meters. Beyond that, conventional surface pumps cannot lift water without specialized design, such as submersible configurations. All pumps, regardless of size or application, operate based on one fundamental principle. They create a pressure difference between inlet and outlet. However, not all pumps achieve this in the same way. There are two primary categories of pumps: positive displacement pumps, which physically trap and move a fixed volume of liquid per cycle; dynamic pumps, which transfer energy to the liquid through motion, most commonly using a rotating impeller. These two approaches are fundamentally different in physics and performance. To truly understand how pumps work, we must examine the two dominant engineering philosophies behind fluid transport: positive displacement and dynamic centrifugal pumping. Although both create a pressure difference between inlet and outlet, the way they add energy to the liquid is fundamentally different. Positive displacement pumps, moving a fixed volume. A positive displacement pump works by physically trapping a defined volume of liquid and forcing it from the suction side to the discharge side. Imagine a syringe. When you pull the plunger back, the internal volume increases. Pressure drops inside the chamber, and atmospheric pressure pushes liquid into the syringe. When you push the plunger forward, the volume decreases, pressure rises, and liquid is forced out. Industrial positive displacement pumps operate on the same principle, but with mechanical precision. In every case, the pump captures a specific amount of liquid and mechanically displaces it. The defining characteristic of a positive displacement pump is this: flow rate is directly proportional to rotational speed and largely independent of system pressure. If system resistance increases, the pump will continue trying to move the same volume of liquid. The pressure will rise accordingly. This is why relief valves are mandatory in positive displacement systems. Without a pressure relief mechanism, the system could fail mechanically due to excessive pressure. Advantages of positive displacement pumps: high pressure capability, accurate flow control, effective handling of viscous fluids, stable performance at low flow rates. Disadvantages: pulsating flow in some designs, mechanical complexity, sensitivity to solid particles. Centrifugal pumps. Transferring kinetic energy. Centrifugal pumps operate on a completely different physical principle. Instead of trapping a fixed volume, they use a rotating impeller to accelerate the liquid outward through centrifugal force. When the impeller spins, liquid enters at the center, the eye of the impeller. As it moves outward along the rotating blades, it gains velocity. This increase in kinetic energy is then partially converted into pressure energy inside the volute casing or diffuser. In simplified terms, mechanical energy from the motor, rotational motion, fluid acceleration, conversion of velocity into pressure. Unlike positive displacement pumps, centrifugal pumps behave differently under changing system conditions. As system pressure increases, flow rate decreases. This natural performance curve allows centrifugal pumps to adapt to variations in system resistance without generating excessive pressure. Advantages of centrifugal pumps: smooth, continuous flow, simple mechanical design, low maintenance, suitable for high flow rates. Disadvantages: lower pressure capability compared to displacement pumps, reduced efficiency with highly viscous fluids, risk of cavitation under poor suction conditions. The fundamental difference: a positive displacement pump works by changing the volume of a chamber. A centrifugal pump works by changing the momentum of the liquid. One physically pushes liquid forward. The other accelerates it and converts velocity into pressure. This distinction determines how each pump performs in real systems. Understanding pump mechanics is only half the story. The real behavior of a pump is determined by fluid dynamics, by how pressure, velocity, elevation, and friction interact inside a complete hydraulic system. At the core of pump physics lies the concept of total head. Head is not simply height. It represents the total mechanical energy per unit weight of the fluid. It combines pressure head, velocity head, elevation head. A pump increases the total head of the liquid. When a pump lifts water to a higher elevation, it increases potential energy. When it forces water through long pipelines, it overcomes friction losses and increases pressure energy. When it accelerates flow, it increases kinetic energy. These three components are linked through fluid dynamics principles often expressed through the Bernoulli equation. In real systems, however, energy is constantly lost. Losses occur due to friction between fluid and pipe walls, turbulence bends and fittings, valves and restrictions, surface roughness, internal hydraulic losses inside the pump. The longer and narrower the piping, the greater the friction losses. This means that pump selection cannot be based solely on required vertical lift. Engineers must calculate total dynamic head, which includes elevation plus all system losses. Pump performance curves, where theory meets reality. Every centrifugal pump has a performance curve that shows the relationship between flow rate, head efficiency, power consumption. At zero flow, the pump produces maximum head. As flow increases, head decreases. Somewhere along that curve lies the best efficiency point, BEP. Operating near the BEP ensures maximum efficiency, minimum vibration, reduced mechanical stress, longer service life. If a pump operates too far from this optimal point, several problems can arise: excessive vibration, overheating, shaft deflection, increased bearing wear, reduced energy efficiency. This is why correct pump sizing is critical. Oversized pumps waste energy. Undersized pumps operate under stress. Cavitation, the silent destroyer. One of the most dangerous phenomena in pumping systems is cavitation. Cavitation occurs when local pressure inside the pump falls below the vapor pressure of the liquid. When this happens, vapor bubbles form inside the fluid, even if the liquid is not boiling in the normal sense. These vapor bubbles typically form near the impeller inlet, where pressure is lowest. As the bubbles move into higher pressure regions, they collapse violently. The implosion creates localized shock waves and microjets that strike metal surfaces. To prevent cavitation, engineers calculate net positive suction head, NPSH. NPSH ensures that sufficient pressure exists at the pump inlet to prevent vapor formation. Maintaining adequate NPSH requires short suction piping, minimal bends, large pipe diameter, proper pump placement below liquid level when possible. Cavitation demonstrates that a pump is not an isolated device. It is part of a dynamic system where pressure and velocity continuously shift. Now that we understand the physics, head, flow, efficiency, cavitation, we can see pumps not just as rotating machines, but as critical components of entire systems. A pump never works alone. It works within a network of pipes, valves, tanks, heat exchangers, and elevation differences. Its behavior is always defined by the system it serves. Residential systems, small device, critical function. In a home water supply system, a pump maintains pressure so that water flows when a tap is opened. The pump does not continuously force water upward. Instead, it maintains a pressure balance in the system. In heating systems, circulation pumps keep hot water moving through radiators or underfloor heating loops. These pumps do not lift water vertically. They overcome friction losses in a closed circuit. Modern residential pumps use variable speed drives. Instead of running at full power constantly, they adjust rotational speed based on demand. This dramatically improves energy efficiency. Automotive applications, continuous thermal control. In internal combustion engines, coolant pumps circulate antifreeze through the engine block and radiator. Without constant circulation, engine temperatures would rise rapidly. Fuel pumps must generate precise pressures to feed injectors. In modern direct injection systems, pressures can reach hundreds of bars. Electric vehicles rely on pumps as well, for cooling battery packs, power electronics, and electric motors. In all cases, pump reliability directly affects system safety and performance. Industrial systems, massive energy transfer. Industrial pumps move thousands of cubic meters of liquid per hour. They are used in water treatment plants, power generation facilities, chemical processing plants, oil refineries, wastewater systems. In these environments, even small efficiency improvements translate into major energy savings. Since pumping accounts for a significant portion of industrial electricity consumption worldwide, optimizing pump performance is not only a technical issue, it is an economic and environmental one. A pump that is too large will operate inefficiently and consume unnecessary energy. A pump that is too small will be overloaded and fail prematurely. A pump is not simply a device that moves liquid. It is a machine that converts rotational mechanical energy into controlled hydraulic energy. It increases pressure. It overcomes resistance. It enables circulation. It makes modern infrastructure possible. Without pumps, there would be no municipal water supply, no cooling systems, no fuel injection, no chemical processing, no large-scale irrigation. From small residential systems to massive industrial operations, pumps are fundamental to civilization's ability to control fluid movement.